Welcome to today's SCA webinar on subsurface compartmentalization, hydrocarbon trapping, and CO2 sequestration with Dr. Salim Shaker. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So let me launch our first polling question. And the question is, what is your primary discipline? We're starting to get the results. We have quite a few geoscientists in the audience, a few petroleum engineers, and a few petrophysicists. So it looks like most of you have voted now, so I'll go ahead and close the poll and share the results. We have 85% geoscience, 8% petroleum engineering, and 8% petrophysics. So our other question is, how many years of full-time experience do you have in the upstream oil and gas industry? So we're starting to get our results now. People are still voting as they're joining the webinar, so numbers keep going up. Looks like we have a good range of different experience levels. Still a few people joining. How many years of full-time experience do you have in the upstream oil and gas industry? Looks like most of you have voted now, so I will close the poll and share the results. We have 47% have over 30 years, 20% have 11 to 20 years, 13% each in the 21 to 30 and 1 to 10 year range, and 7% with less than 1 year. So thanks for providing us with some demographics of our audience. And before I introduce Salim, I'd like to remind the audience that you're muted, but you can ask questions during the presentation using the GoToWebinar question feature. We will cover the Q&A at the end of the presentation, and you will be anonymous. I'd like to share some slides here, so let me pull up my slides. So again, the title of today's presentation is Subsurface Compartmentalization, Hydrocarbon Trapping, and CO2 Sequestration. And our speaker today is Dr. Salim Shaker. Salim received BS, Master's, and PhD in Geology from ASU in Egypt. He also has a diploma in Hydrology from Prague University. More than 35 years in the oil and gas industry. He's worked on projects around the world, and he's published more than 40 papers and is very involved in a number of professional societies. He was chair of the Pore Pressure Session at APG 2014 and chair of some deepwater geoscience workshops between 2010 and 2016 for APG. He's also received the Atwater Award for his paper, A New Approach to Pore Pressure Prediction in the Gulf of Mexico.
Susan, we're not seeing your screen.
All right, let me try sharing again.
Flashed on.
All right, let me try again. Do you see it now?
Yes.
Okay, thank you, Mary. So the course that Salim is teaching in August in SCA's training center is Seal and Reservoir Pressure Analysis for E&P Prospects. And you can see the description there. That's August 19th through 21st in Houston, Texas. There's also a course scheduled in December on pore pressure, fracture pressure, and wellbore stability in Houston, Texas, December 9th through 13th. And he also teaches courses including formation pore fracture predictions and measurements from the exploration prospect to the wellhead, for safe drilling, formation fracture predictions, pressure interpretations and analysis, pore pressure, fracture pressure, and wellbore stability, and seal and reservoir pressures analysis for E&P prospects risk assessment. We have several webinars coming up in the next few months. In August, join us for a webinar from Dr. Dennis Drea on fiber optics, getting it right with fiber optics from monitoring frac growth to managing well integrity. In September, Dr. Joan Rosine on deep water in 2024, science, technology, and valuation. And in October and November, we will have Ellen Cooper-Smith and Ray Spence with two webinars. The first one is on decision framing for project management, building quality field development plans. And the November webinar is the value of information, the MIN kit, justifying information and the tie to future decisions it impacts. Please join us for a live online course that's offered in October, featuring Dr. Larry Lake and Dr. Jerry Jensen on managing mature oil fields with CRM, capacitance resistance modeling. And of course, all of our training classes can be offered in your office, in-house, in a private location. Some of the classes are available live online, and others are offered in our office in a public venue in SCA's training center. In addition to training, SCA also offers consulting and recruitment services. So I'm going to pass the presentation rights over to Salim, and you should have that now.
Can you see the screen?
Not yet. Now we see it.
Okay, good. Well, is it okay now?
You're good to go.
All right. Thank you, Susan, for the introduction. And I do thank everyone of the attendees. And I'm trying to get my presentation. Here you go. This is the first slide. So this segment here, which is the compartmentalization for the hydrocarbon and the carbon sequestration, is very tiny segment in the whole course, but this is probably a very important segment. So therefore, I choose the webinar to give you some highlights or snapshots what that course is going to look like. So the concepts and the model of the course has 7 items here. You can see them here. So I just go and elaborate on that compartmentalization. And that's what I'm going to. For hydrocarbon entrapment, compartmentalization is very important. Compartment in our business, in the oil and gas business, the compartment definition is to receive hydrocarbon, keep it for 10 million years, 15 million years, and then when we drill to it, it delivers. That's a compartment. Some of these compartments, it does breach, does not keep all the hydrocarbon. So we're gonna see how we can predict or see it sometimes. Is it progressive or regressive? We're gonna go through four-way closure versus full to three-way, and how the entrapment take place. And then I have to go through the hydrodynamic as well, because there's a lot of hydrocarbon around the world, some of them in the Middle East, but a lot of hydrodynamic traps exist, and I study some of them in South America. And the last one with the geopressure system, that's a tricky one, and I'm gonna elaborate. Maybe I give it about 5-7 minutes on the last chapter. So let's go. We see what is the deal with build up pressure with stress. What we need stress. First of all, sediments come from the continent, deposit in the deltaic system, in the sea or in the ocean, and then they start compacting. That compaction within the fine layers or sediments, how it looks like water. We need fluid, and we need porosity. So you got the stress, you got the fluid, and the porosity. The three of them is needed to build up pressure. And build up the pressure, that's what gives us either a good trap or breach trap. During the compaction, most of the fluid goes out, and that's we call it the expelled water. Some of them stay in, cannot released by stress, and reach point to the top of the geopressure build up here. This is when the seal start form itself. So here is opened, here is sealed, and here is what we came up with the idea of the effective stress, because here is the fluid pushing against the grain, and the grain pushing against the fluid, and that's what the porosity change from increasing to change direction. Instead of increasing, is decrease. And based on that, the velocity also is gonna do the same thing. The velocity is gonna increase, and then it's gonna freeze at the top of the geopressure. On the 1930s, that's way, what, 100 years ago, this guy came up with the exponential trend for the compaction, and we're still using it. So the fine material and the shale and the clay, they are compact and exponentially. So we have two lithologies here. We have the sand and the shale. Okay, I'm talking about now sedimentary rocks, clastic rocks. I'm not talking about limestone. I'm not talking about anything else. So here is a column of sand and shale. And let's see what the behavior looks like during the compaction and how we're going to form compartments. So here is your shale. Here's your sand, that round grain. And with the stress and the heat, and that's overburden, increase the stress, increase the heat, the fluid is gonna run away from this part here until it reach the point where they stay. This is why I call it the compaction trend. This is not a normal compaction trend, it's just a compaction trend, because sediments in the process of compacting, and the fluid is running away to the surface. Here is the top of the dew pressure. You go down here, the fluid within the sand is fast. It has permeability, has pressure differential. In the shale is not. You can see the difference between the pressure in the sand here is linear, fast, in the shale exponentially. And another layer, another sand. Here is going fast, stop, fast, stop, go slow, fast, stop, go slow. This is the main cause or the main root of forming compartmentalization. So what do you see here? You see the hydrostatic, and you see the pressure here in the sand going in a different compartment right here. And so the shift between each compartment is the shale pressure, which is the fluid compressed from the shale. From the first slide we saw, the fluid compressed from the shale, going to the sand, moving fast, jump to another sand layer. That's what compartment looks like. And that's the right way understanding the compartmentalization. I took the initiative and the courage, and I changed the whole system. I said, well, the subsurface system is not two compartments, it's not normal pressure and geopressure. The subsurface system is 4 zones. Here, a zone just fresh coming out of the river or from the onshore. Here, the zone which is the compaction take place right here. So the fluid is moving. This is the dynamic. And then here is the zone it's gonna cap everything below. And this is the geopressure system. So I divided to four zones. I'm building a lot of ideas about it. Here is the exponential trend for the shale. Here is the linear trend for the sand. And that's what the compartmentalization looks like. This is a mechanical model. If we have a cylinder, so fill it up with water, whatever, salt water or fresh water. Here is your gradient. By the way, the gradient is the change from one point to another point is not depth related. And I have some slides on LinkedIn to explain the difference between gradient, which is the pressure over depth, or the gradient between 2 points. The gradient is between 2 points. It's not a depth. It's not a value over depth. So here is the gradient if this cylinder is wide open. If we divide the cylinder to 4 small cylinders right here, and between them there is a seal right here. So the first one is going to have hydrostatic. The second one is going to carry the first cylinder plus the hydrostatic. It's going to shift to the right. The third one is going to carry 2 and hydrostatic, shift to the right, and so on. That's what compartmentalization is. And here is the seal. If you look at the seismic line, a seismic line, no faults, nothing, just depositional, continuous deposition. And that's what you're going to see. You're going to see the seal pressure going exponential, the reservoir going linear, exponential, linear. And actually, if you look at the petrophysical properties as sonic, velocity, or resistivity, you can see the trend. The trend stay there in the sediments, even after buried for 20 million years or so. So that's what the pressure envelope form between the compartments, and shift from one compartment to another compartment It gives you an indication that this compartment either sealed or not sealed. This is, I made this plot probably about 23 years ago in the GCAGS, and I encourage everyone to have a plot drawn like this. This is a hydrostatic, this is a principal stress or the lithostatic, and here is the pore pressure. The pore pressure has to be or should be divided to two parts. This is the part in the shale, and this is the part in the sand. And the sand is measured, and the shale is predicted, and you see the compartmentalization. You see sand, shale, you see different compartment. But I used to work for a consult for a software company, knowledge system, and we used to sell a lot of software. So it's the easy way for anybody to have a last file and a software and just dump the last file on the software without distinguish between sand and shale. So what do you see? That's what it is. I did not have the reference here because it's not my business. So somebody have fun here or has fun or had fun. He has some, here a gamma ray, here a VP, here is the density, and he just, or he or she, or the software itself, well, actually the software did, that's the prediction of the pore pressure. Although there is a measured pore pressure here, right here. How you measure pore pressure here and you predict it? Pore pressure does not predict it in the sand. It's measured in the sand. Anyway, that's what we need to always distinguish between the pressure in the sand and the pressure in the shale. Here is a generic plot, and I would say in here the compartmentalization for safety. Very important to have compartmentalization assignment in the subsurface for safety. Here is your pore pressure, the usual, linear, exponential. Here is your frag pressure, right here. And between the mud, the pore pressure and the frag pressure, you do have the mud. I'm glad we have some drilling engineers in the group. And the mud here, measured in ECD or ESD, either static or dynamic. The dynamic means in the movement. The mud is moving, going from the direct floor down to the drill bed, coming back. So it has the pressure of the pump added to the static. So if the trip margin is required now by the MMS or the BOEM, that your mud cannot go below the pore pressure. Actually, the mud has to be about between a quarter or a half a pound above the pore pressure to prevent the flow or the kicks. Over here on the frag pressure side, they have something they call it the kick tolerance. So you cannot approach with the mud. You approach the point where your mud pressure or the ECD very close to the frag pressure. You have to have leave a little window between the frag pressure and the mud weight. And this is the kick tolerance. This is the drilling tolerance window. I did that maybe about 15 years ago. And compartmentalization for safety as well. It's not just for hydrocarbon accumulation. In this case, we might have a kick, hard kick. In this case, we might have a leak. We might have a loss of circulation. So compartmentalization is good to look at it, study it, get your petrophysical properties, the software, where is the sand, where is the shale, and where is the communication point, and where is the sealed part of the subsurface. Here is there a fault here, the same cylinder, we're gonna put the fluid in it. That fault is gonna do a communication between those two compartments right here. So let's see what the pressure plot is going to looks like. These guys here, those two chambers here, in communication right here. And we're going to see examples from the RFTs, MDTs, that show that communication is between the two of them. And we call it breach seal. 20 years ago, when we used to have a group of companies, we get together and we find out why our prospect was not good. Dry holes. Why was it dry hole? And despite it has uh, all the geophysical indication, the AVO and everything justify the presence of hydrocarbon, but was dry because the compartmentalization, because the compartment was breached. And the justification just breach compartments. And nobody look at it why it's breach. Here is the breach. So you got your pore pressure in the shale going forward. And then when the breach took place and the sand here communicate with the sand up here through the fault right here, what happened? The shale start to have the effect. So instead of the porosity or the pore pressure going forward, it goes backward. And also the petrophysical property. You can see a little reverse before you hit a breach compartment. And you see the breach compartment was this the target. And the target is wet, not was. Here is a I show this example a lot. Here is a basin, they call it the Auger Basin, the Gulf of Mexico. One side of the basin, we have all kind of discoveries, macaroni, oregano. This is the not deep water, just kind of just off the shelf, like 400, maybe 600 feet water depth. And then here is a seismic line between macaroni and this dry hole. This dry hole, when somebody bought the acreage here and drilled a well, that block has a bet of $40 million. Because if you look at the seismic line here, here is your field. Extrapolate that line or this zone up to here. Here is higher than here. And there a closure, good closure, right here. And lo and behold, they drilled this as wet, dry, nothing in it. The story is, that's going to come in the course as well. The salt timing, the salt intrusive timing. By the way, this is in the Gulf of Mexico here in Auger Basin. Over here, this is Zama, the discovery on offshore Mexico. And they have a little similarity here if you look at it. You see that beauty of the seals. See that pinch out and the seals. He didn't see it. Same thing here. But the trick was what? The salt in this side here was growing during the load of the sediments. So the salt go up gradually, probably an inch a year, 2 inches a year, and the sediment lay on the top of it. So the sediments start pinching out. Over here, the salt intervened or came in the system in probably a million year period. Just cut through and went up. It was very fast. So this is impingement and this is a ridge. So also compartmentalization, I was going to see sequence stratigraphy is a guide to tell you where is your breach seal from a competent seal. Here is the sequence stratigraphy also to tell you about compartmentalization. Here we have 1, 2, 3, 4 layers here. This is porous and possible reservoirs. Okay, the upper one here is not enough time to get hydrocarbon in it. But what we see here, we see a communication right here at this point here from the seismic. So if we look at the velocity here, I'm glad we have some petrophysicists. Here is the velocity increase with the compaction, and then start reverse itself. So our seal is here. We have a seal here, top seal. Yeah. And then we do say what? Based on that, we predict the pool pressure. We see this pool pressure here. Looks like, you see, notice here is no pool pressure prediction over here because this is sand. We're not supposed to predict pool pressure on it. And then I give this to the drilling engineer, thanks to the drilling engineer, and say, well, here is our predicted pool pressure, add half a pound, and here is our mud weight. So they designed the mud weight. When they designed the mud weight and everything nice, and we start drilling the well, we might receive a hard kick here. And over here, we might receive a loss of circulation. Why? Because this is a transgressive compartment right here. The pressure increase. Here it goes back. Why it goes back? Because this guy here, number 4 and number 2, they are talking to each other here. So there are communication. This is the reservoir and seal limits for hydrocarbon. This is like any other plots. You got hydrocarbon, you got hydrostatic, overburden, principal stress, and the usual shale, sand, shale, sand, and so on. And we have a seal here. So here is the frac pressure. How much hydrocarbon can we trap here? If we have 4-way closure, not 3-way, 4-way. 4-way means it's like this. We're gonna see example pretty soon. 4-way. What are we gonna see here? If we have oil and gas, here is the gradient of the oil. Remember, I'm talking about gradient, not slope. Here is the gradient of the gas. I'm taking the gradient of the gas, put it here. I'm taking the gradient of the oil, put it here in this compartment underneath the seal. And here is my pore pressure. Here is my frac pressure. If I extrapolate that gas trend down to here, this is the only column of gas I can trap. On the other hand, because the oil has a lower slope, it's not as steep as the gas, I can have more oil in the same trap than gas. And that's why now in the deep water, we discover more oil than gas, because the deep water has a drilling window or drilling tolerance window, narrow drilling tolerance window. The frac pressure is close to the pore pressure. Therefore, our windows in the deep water of retaining a hydrocarbon is narrow. Therefore, we found more oil than gas. So this is part of the compartmentalization. Why we find this, we don't find this. And here is the sealing capacity. I call the sealing capacity the jump from one compartment to another compartment. This is a compartment, this is another compartment. The jump is sealing capacity. You have a jump, or you have a very good uh, uh, pressure ledge or ledge ramp. I'm sorry, seal ramp. Okay, so I mixed it up between ramp and seal, and okay, that's not remind us anybody. But anyway, here is the four-way closure here, structure closure, and the same we saw here. I just put the closure on the top of it, right here. Here's our seal. Here our gas. Here our oil. What is that? Can that help in doing anything? If the structure relief is higher than the retention capacity, here is the retention capacity, which is the difference between the frac pressure and the pore pressure. If the structure relief larger than that value here, you can trap as much as you can in that closure until you hit the spill point. We're gonna see an example soon. Here is the gas, here is the oil. I'm just enlargement of that previous slide. I just put it in a zoom mode. Here is the retention capacity. Here is the gas. Here is the oil. An example, Jack Discovery, Jack Field, has about 2,000 or 3,000 feet of oil, because the structure closure is higher than the RC, retention capacity. That's another zoom. What is that? If I drill in the geopressure compartments, is it more profitable than drill above the geopressure? I said yes. In the geopressure system, because you have a hydraulic head. The hydraulic head, it is the extrapolation of the excess pressure. Here is the excess pressure here, in addition to the hydrocarbon column. You add them together and they give you a hydraulic head. That's why we have strong kicks and we have blowout, because you have a hydraulic head. If we don't have a hydraulic head, we're not going to have a blowout, right? We're going to have a strong kicks. So this is the advantage of finding hydrocarbon in the geopressure compartments. In the geopressure compartments, you can drill a well and the well produce for many, many years, just natural flow. It just the pressure drop, but does not reach that hydrostatic system here easily, because you have a hydraulic head. I did work on when I used to work for Phillips. I worked on one of the fields in High Island, and that field was drilled in the 1950s, 58, 59. I, I work on the development side of it. It's very interesting. Some of the wells was producing for 40 years because was tapped the geopressure system. If you have hydrocarbon in the above the geopressure system, that's what I'm showing you above the top of the geopressure. It's not going to be strong. Yeah, you can have production and everything, just very weak production. You can see the graph here, how it looks like. It is the gas, oil, hydrostatic, the pool pressure, and frac pressure. And in the early 1990s, there are a lot of companies in offshore Louisiana and Texas. They were just chasing the shallow amplitude anomalies, and they drill well. They make good money, but the well fizzle out in 3-4 years. No more production. So that's the difference between in the hydraulic in the hydrodynamic system and the geopressure system. It doesn't mean you have a thick shale, you have a good sealing capacity. No, because in this is from the Gulf of Mexico, a well, deep well in the Gulf of Mexico. You can see here you have a good seal. Here you have a fat, big, thick shale, but doesn't have a big seal. If you have any prospect here, this is very high risk prospect, because if you look at the RFTs or the MDTs, straight data communication here. This says skinny one S4 is good. It's a good prospect location or zone. If you have hydrocarbon here, or if you have a prospect, drill it, and your risk is very low. That's the advantage of study compartmentalization. Here is this is the same slide I showed before. Here is how to calculate your gas column and your oil column here. Compartmentalization also is not vertical, it is horizontal. And this is field from the North Sea. I have the permission to copy this from the Geophysics 203, and you see the gradient here across the fault of the pressure gradient is completely different. So here is onshore as well, here in the US of A, and you see across the fault the pressure gradient is different, and therefore you have a compartmentalization, horizontal compartmentalization. You can call it lateral compartmentalization. So compartmentalization could be vertical or horizontal. Could be both, right? Here is the risk assessment of hydrocarbon compartmentalization due to fault system. Faulting. Most of our prospects rely on faults, either three-way, most of them three-way. Okay. So let's look at this. Here is the big fault here. What's the chances of trapping hydrocarbon? Number one, if your fault displacement 200 meter, okay, and your sand juxtaposition is the sand thickness is 200 meter, so the only hydrocarbon you're gonna trap in this compartment here is this part here, because the thickness of the sand and the fault displacement. So only you're gonna have 200 meter of hydrocarbon. If you believe that shale smear can form a seal, I'm sorry, I don't believe in it, but I put it because a lot of people think shale smear can form a seal. But if you have a gouge in that shale smear, all your hydrocarbon is going to go through this gouge. Even if the gouge is 10 feet and the shell smear, all your hydrocarbon is going to, your maximum capacity of the compartment is till when you hit the gouge, right here. If you have a fault critical pressure, which is part of the course as well, is your compartment or hydrocarbon compartment is bigger a little bit because the fault is going to open up later. But if you're lucky enough and you have a huge closure and large sealing capacity and retention capacity, here is your compartment is going to be huge right here. And the only time or only place the hydrocarbon is going to spill along with the spill point right here. So compartmentalization is good. Okay, here is the DHI. If you have a bright spot. Fault also. It has a direction and in relationship to the sediments itself. You got antithetic faults, synthetic fault. I do like the antithetic faults. So you can see the spill point here. You got more reserves here. Here the synthetic faults, it breach easy. Here is synthetic. You see the fault dipping this way and the sediment dipping this way. Over here, the sediments and its fault dipping in the opposite way, the antithetic. This is a good compartmentalization for hydrocarbon trapping. This is the when the fault, okay, this part here, the fault critical pressure failure, this is part of the calculation in the course as well. It is your pour pressure for wet sand. You add the gas to it, and you have, we just gas case, and here the Shemin or the leak off test. So this is the frag pressure, this is the pour pressure, and the fault between the pour pressure and the frag pressure has a window, and this is the fault leak window. The fault is not a conduit in the subsurface. It's not an open pipe. The fault still sealed, but the fault opened as a faulty valve. Faulty valve means when the valve reach the fluid behind the valve opened, reach a certain pressure, the fault opened, spilled that extra fluid, and closed back. That's what it does. Is burb. Fault always burb. If you are from the old school and you went to Galloway School in the Mississippi Delta, you can see the gas coming out of the ground. It's bubbling because there are fault there, and it just bubble. It's burb, bang, bang. So that's how that hydrocarbon come out of the ground from that trap up to the surface when the fault open. I'm gonna speed it up a little bit. Let's go to the okay. Now let's leave the hydrocarbon. Okay, that's gonna be in the class. Everything in the class is gonna be there. Risk assessment, how much hydrocarbon we can trap. Let's see how we can store hydrocarbon. Yeah, in the subsurface. Is that safe? Is that good? Where we can safely store it. So should we store hydrocarbon in a depleted oil and gas reservoirs? Okay, we go to abandoned field. and say, well, we're going to store hydrocarbon here. Should we store it in a near hydrostatic pressure or depleted pressure? Or should we use the carbon dioxide for oil recovery, which is kill two birds with one stone, produce more oil and store carbon dioxide? Or can we do it in a hydrodynamic system? Is it dangerous to put it in a hydrodynamic system or not? Or, as I do prefer, put it in a geopressured compartments. Here, as we saw that before, I have a hard time to get the density of the carbon dioxide, because carbon dioxide density, wide range, goes from vapor to gas to solid. So I have a hard time to put a window here. So you have the oil window here, you have the gas window, and I try to put the carbon dioxide in between, but it depends how deep you're gonna store the hydrocarbon, how much pressure you're gonna have to put it on the hydrocarbon to store it. Here is here is the case history from Vascanol Block 912. Here is transgressive compartment. Here is a regressive compartment going backward. And here is transgressive compartment. Should I put carbon dioxide in a regressive compartment? No, because it's going to go somewhere we don't know where. So compartmentalization is good to look at it, study it, to decide if you want to put carbon dioxide where in the section. See, this one here is regressive as well. It's not as safe to put it in. This is in communication. I will not advise anybody to put any carbon dioxide in Vascanol 1001. In the hydrodynamic system, is it advisable to store carbon dioxide in the hydrodynamic system, which is a lot of hydrodynamic system nearby industrial areas? I do not advise this because some of them are static, which is possible good. There's a good compartment for carbon dioxide. Some of them is dynamic. This is, you put carbon dioxide in any part of the reservoir, is gonna go to the surface. Here is hydrocarbon in the dynamic versus static. Static, this hydrodynamic. If you have a water source here and you push the hydrocarbon away, so the same thing is going to happen to the carbon dioxide. This is an example from the North Sea. I don't think the North Sea will be used because some people talk about putting carbon dioxide in some of the old reservoir in the North Sea. Anyway, I hope that you guys gain some benefits. I wish I had more time because we're getting close to the quitting time. Here is slide from SCA, and I've been consulting for them for 20 years, and I'm happy about the whole staff and everybody. So I wish you well, and if you have a question, I will be happy to answer your questions. Thank you.
Thank you, Salim. Now we have some time for questions. I'd like to thank everybody for attending today's webinar. You can put your questions in the GoToWebinar question feature. Later today, you will receive a link to a recording of today's webinar, an evaluation form, and a link to register for seal and reservoir pressure analysis for E&P prospects that's scheduled for August 19th through 21st in SCA's Houston Training Center. So, Celine, can young sediments still under the compaction process be a safe place for carbon dioxide storage?
Well, this is a good question, Susan. Yes and no. It depends where the young sediments is. I mean, it can be under one condition: if the young sediments is gonna, the compaction is not long-term compaction. You know, like trying to say, if you have a marley sediments, or because not everywhere there is sand and shale. If you have a marley sediment, so it could be, it could be a possibility, but it's still a little bit iffy because you're still under the compaction. And no, I will be careful to use it as a uh, storage for carbon dioxide.
Next question. When you mentioned about putting CO2 in the geopressure interval, does that mean you store it in an overpressured zone? If yes, how do you
Yeah,
manage the storage capacity, as injecting CO2 would be adding pressure to what is already a saturated interval?
well, what happened here when you have a regressive system, if you have a regressive system here, let me see that slide here, right here, right here. That's what are we talking about? Okay. If we have a regressive system, this is not, it is overpressure, but this system means it has a leak or breach somewhere up to the lower compartment, and is not desirable to put any uh, storage or carbon uh, dioxide in that system. And the problem is carbon dioxide, you don't know how far that the column is, because under certain condition the density of the carbon dioxide change. That's what I mentioned, go from vapor to gas to solid. You can buy it from the grocery store as solid. You know, you want to pack some stuff to send it or somewhere in 1 day or 2 days and keep it cool. You buy carbon dioxide, frozen carbon dioxide. So I'm not encouraged that in a regressive system you put carbon dioxide. However, in the progressive system, and like here, and you have some oil and gas has been produced, yes, your excess pressure goes down a little bit because you produce the excess pressure from the overpressured compartment. This is an overpressured compartment as a just fresh water compartment. It has no hydrocarbon. When you add the hydrocarbon here, you add that 400 psi here as a hydrocarbon. But when you produce this zone from the overpressure zone, you take that 400 psi away and you can replace it with carbon dioxide. Yeah, I think this more safe. Yes.
Next question, how does voidage in a closed system play in? Does CO2 remain liquid under high reservoir pressures?
This is the this is the 1 million question, $1 million question. I don't know because I read so many articles and mathematics and all the good physics about how far that carbon dioxide is going to stay in the gas phase and under what condition, temperature and pressure. I don't know, but I can answer that question perfectly, but it's still unknown because I could not put my hand on how that density change with pressure and temperature of the carbon dioxide. There's a lot of research about it, but was way above my grade.
We still have a lot to learn.
Yes,
So I'd like to thank everyone for attending today's webinar. Later today, you'll receive a link to the recording of today's webinar, an evaluation form, and a link to register for seal and reservoir pressure analysis for E&P prospects scheduled for August 19th through 21st in Houston, Texas. Thanks for joining us today. Goodbye.
thank you. Thank you. Thank you, everybody.
Bye.